Hi, my name is Nate Gearin, and what you're about to see is the final project presentation for CSCIE 95 Compiler Design and Implementation at Harvard Extension School, taught by Dr. James Frankel and assisted by Daniel Williamson and Mark Ford. Over the upcoming 10 minutes or so, I'm going to demonstrate different parts of my compiler, and at the end we'll be available to answer questions. So I hope you enjoy. Before I get going into the different parts of the compiler, I want to demonstrate the compiler working, compiling a source file. So I've pulled up a Fibonacci sequence implementation. You'll see up here on line 1 the declaration of the Fibonacci function that takes an int, which represents an index in the sequence to look up, and returns an int. Main loops forever here, asking the user to give it an integer. And when it gets that integer, it then calculates the value using that integer as an index into the Fibonacci sequence and loops back to the top. Fibonacci is implemented with the base conditions of 0 and 1 returning itself immediately. Otherwise, it makes 2 recursive function calls to look up what the values of the indices 1 below it and 2 below it are. So it's pretty standard. It's a pretty standard recursive implementation. To give you a demonstration of what the output looks like when I compile it using my compiler, you can see at the top there's a data section and then the text section below. And were I to compile it, I just threw out the assembly output into a file called a.s. I'm going to run it here. And it asks for an integer. I'll say 4, and it tells me that the value is 3 when the index is 4. And let's try 10. It's 55. Once you get to larger numbers, because of the recursive implementation, it takes a second to chug an answer out. Yep, and there it is. At the beginning of the course, Dr. Frankel made the statement that for a lot of us, this would probably be the largest program that we've written to date. While I can't say that it definitively is for me, I can say that it feels like it's among one of the largest. And when I looked at actually the number of lines of C code that I wrote, it turned out to be something around 10,000 lines of code after excluding the generated C code from Flex and Bison. And as I was writing a lot of this code, it became apparent early on that I really needed to have tests for all of the different things in my compiler, because as the compiler progressed through staged operations, the output from an earlier stage affects the input from a later stage, and in these types of situations it's really easy for a change in an earlier stage to sort of ripple through the compiler and cause bugs in a later point in the process. So from problem sets 1 to 3, I had a sort of basic testing package that I created where I was creating these input files and then these output files like this. This was for a symbol table test, and then I would have bash run the compiler at, for example, the symbol table stage, check the output and compare the actual output to the expected output. I found this to work very well for the first couple problem sets, but as I progressed along, I realized that having these types of integration tests weren't really scalable as the amount of code that I wrote increased. So I then took Mark Ford's advice and incorporated Google Test into my testing framework. And I created all of these really nice functions that allowed me to test things really easily over the course of the semester. So for example, the signature of this one function that I created for the optimization phase is a function that takes 2 different IR lists, and what it does is it compiles them into 2 different MIPS files and then runs both of those files on the SPIM emulator and compares the output from the SPIM emulator to make sure that the output from the unoptimized and the optimized IR is the same. I did all of this using standard system calls in Linux, and you can see it allows me to write really concise tests for testing optimization code. So here I just take one source file from a file and remap that to standard in. I then generate both non-optimized and optimized IR from that source file, and then I just run this function over the two different versions of IR and expect the output to be the same. And if not, the test will fail, giving me really immediate feedback. Another example would be how I tested IR. I created these helper functions that allowed me to extract IR from a particular node of the parse tree. For example, here I extract the IR from the first binary expression in this file that I create. I have here this function with greater than equals expression constant.testin. I then assert that the IR that's created matches this IR exactly. Over the period from problem sets 3 to now, I've written exactly 341 Google tests, and what's really cool is that they run to finish on about a fifth of the second. I want to talk for a minute now about some of the optimizations I did in my compiler. I, in particular, did the coalescing of load address load word and load address store word instructions into single IR nodes that are then translated into single MIPS instructions that calculate the address of variables based off of frame pointers and global pointers, rather than first calculating them off the frame pointer and then actually loading or storing the variable to that address. So to give you an example of the IR that's generated without optimizations, separated into blocks, you see that there's this one block that has two labels at the beginning, and then it has a address of and load word. Now we would expect both of these instructions to be coalesced into a single IR instruction each, which if we look at the program with optimizations, they are. They're coalesced into these new IR nodes, load word from variable, and then later you can see also there's a store word to variable. So what difference does that make in the compilation of a particular MIPS program? A simple MIPS program, for example, that just loops from 0 to 10, printing out an integer. Well, it makes a difference, but it doesn't make a huge difference. In this particular case, it saved around 5% of text instructions, so it got a performance speed up of 5%. Obviously, this alone makes a difference, but not a huge difference. But with other optimizations, it will add always an additional 5%, which is nice. And you can see in terms of what was generated into MIPS, rather than this load address and then store word, there is just directly a store word at 0 off of the global pointer. So this became this. I'm going to talk about one other optimization that I did, and that is a more general dead code removal by computing liveness. So if you look at this program, there are these two lines of code that are essentially pointless. A compiler shouldn't generate any code for them because they don't do anything. But in the mechanical generation of the IR, such as this, you can see that there's two blocks and code for the storing of argc into A is generated. Now, my optimizer recognizes that this code is useless and removes it, and it turns a 10-node IR program into a 6-node IR program, which has a huge savings. This is reflected in the MIPS code as well, obviously because there aren't IR nodes that were there before. I haven't enabled this optimization because it does not correctly trace variable liveness across basic blocks yet. I spent some time working on that and haven't quite tweaked all of the bugs out of it. So it only works in simple cases where there aren't a lot of control flow statements and loop statements. Yeah, so with that, I want to thank you for your attention. I've had a great time in the course, taking all 3 courses, and if you have any questions, I'm here to answer them. Thanks again.